Hi, everybody. Thank you for tuning in. Before we get started, please bear in mind that this should be an interactive experience. So if you'd like to ask any questions, please do so, and I'll try and pick some good ones out. Please be respectful of each other. And if you think you might like to come on the show yourself, then please do get in contact. My contact details on the channel's About page. Next week, we'll be talking to Graham Sutherland about EMF camp and lasers and other things, I'm sure. But today's guest is Matthew Venn. Hello, Matt.
Hey, how's it going?
Yeah, good, thanks. Would you like to introduce yourself, say a little bit about who you are and what you do?
Yeah, I'm Matthew Venn. I'm a electronic engineer and technology communicator, because I always do more technology communication than science communication. And you may know me from past adventures as learning how to make computer chips. That's been what I've been doing the last year and a half.
Yeah, so that's going to be the major focus of our talk today. But before we get into that, are you willing to talk about your background a bit? So uni, for example, you think you studied electronics, and how you got into that?
Yeah, I kind of got into it fairly randomly. I liked making kits and taking apart things as a kid, and I particularly remember having a Velman kit that was you type in a PIN number to get a password, and that would then open my door on my bedroom, stop my sisters from getting in.
Yep.
And I like slowly upgraded it through the years, and I had a little switch on it so I could turn on and off whether it was gonna, like a master override switch. And I'd got some 7-segment displays, and I wired them up manually with a soldering iron so that when the power was on, it said open, and when the power was off, it just didn't say anything because the power was off. And I remember then just thinking, how on earth would you put a word or count numbers on this? Because I had no really idea of microcontrollers or programming or anything at that point. So, and then when it came to kind of university time, I was like interested in science and technology, and just kind of was fairly random. I was encouraged to do something that was practical because I would be more easier able to get sponsorship, which was a thing back then, like an apprenticeship thing, which I did. I got a sponsorship or apprenticeship with GEC Marconi.
Right, well done. Yeah.
So that was like a year before uni, and then working there in the summers, which was a very formative experience actually.
Was that kind of like a gap year, as in you finished college or whatever, did that year and then went on to uni?
Yes, and then every summer holiday I would go to their factory and work, kind of doing different things. And it was very good and very bad.
Okay.
But one of the great things was they sent us on a kind of industrial engineering course, and there was a small team of like 6 of us, and we built a milling machine from scratch where we like cast aluminium parts and milled beds and ground and polished things and built circuit boards and it was looking back on it was astonishing that we did it. It took like 3 months, but in the end we did we're able to cut some patterns out of some plastic. It was pretty fantastic. Amazing. Yeah.
Was that sort of a ground up really milling machine then? You it sounds like you did a lot of the work. You didn't sort of bring in parts as such. It
was like a thing that the people that we were with had devised. So they'd already done things like built the molding pieces, but then we had to do the green sand, pack the molding pieces in, pull them out, melt the aluminium and pour the aluminium in.
Okay.
But we didn't actually have to design those mold pieces.
Yeah. Okay. Yeah. So you went through all the processes and things, which was probably a brilliant experience.
Yeah, and that really kind of introduced me to milling and lathing, which I've got a mill and a lathe in my workshop, and it's still something that I enjoy getting back to take a break from the computer screen.
Fantastic. And then since uni, you've done all sorts of things. So if we touch on music quickly, that's quite a keen hobby of yours by the sounds of it.
It was through university that I kind of saw other people making electronic music, and that kind of sucked me in, and I got a PC and a sound card, and spent all my money on synthesizers, synthesizers and records. I think I was DJing as well.
Oh, fantastic!
And that stayed with me. I've moved away from the computer now. Now I tend to use hardware
Mhm.
again to have a break from the screen. Like Ableton Live on a Mac is, and a sound card is like amazing. You can do anything with it, but it's like,
It's still very computer based, and
yeah, it's like then it doesn't work one day because the disk's out of space, or it gets a virus, or it loses the sync with the sound card, or
right.
and then it's all, yeah, it's just always looking at the screen again. So
Yeah. So we're talking about modular synths and lots of cables and that sort of thing. Is that the direction
I
you're taking?
think I might do if I had loads of space and loads of money. But actually,
Yeah,
the
yeah.
thing that I'm just exploring now is quite a new instrument from a company called Electron, called Syntact, and it's like one box that has 12 synthesizers in it and a sequencer. So
Okay.
I'm just using that one thing at the moment and nothing else.
Nice.
Yeah.
Very good.
Yeah, it's cool. It's fun.
So a while ago, you were living in the UK, and you were actually director of Bristol Hackspace, which is
Yeah, the city
fantastic.
I'm living in Valencia now, and the city I was living in before was Bristol, and I lived there for 4 years, I think, before
Okay.
moving here. I've been here 6 years now. And when I moved from London, I visited 2 places in Bristol, Bristol Hackspace and the Bristol Bike Project,
Right.
and I got involved with both of them early on, and ended up merging all of my tools into Bristol Hackspace, and then kind of becoming a director in the end.
Okay. And so what did that entail, being a director of a hackspace? Is that a lot of organization and safety and all that sort of thing, or is it more hands-on?
I think it really depends on your members. I've maybe visited 8 or 10 hackspaces just in the UK, and you talk to the people that are involved, and it depends on the members and what they're into. And sometimes you can have somebody that's like really health and safety oriented because they've come from like some part of their previous life that's had a massive impact on them, and they're like, you can't just leave these tools out, someone's going to hurt themselves. And then you have like other people saying, that's the whole point.
Right. Fair enough.
Yeah, but as a director, we were looking at like, okay, but then if people do hurt themselves, who's liable?
Yeah.
Can we get insurance? What's liability insurance like for Hackspace? Then like talking to insurance people, and then they don't know what a Hackspace is, and then you're trying to, we ended up with some kind of like artist liability insurance in the end, which
Okay, interesting.
may or may not have paid out.
Insurance is tricky like that, isn't it?
Yeah.
You do your best.
But yeah, then it kind of, focusing on processes like how to welcome people and show them what's available, but also have like a training pathway into a tool like a laser cutter or a milling machine.
Yeah. So I presume, you had laser cutters, for example, or one, and if someone comes along and they join the space and they say, I'd like to cut some
Cut my fingers off.
Yeah. Well, maybe not fingers, but is that something that you had training material, or is it more of this is the experts, spend an hour with them and you find out?
Yeah, we had different people do like in charge of doing different things, like 3D printers or laser cutters or CNC machines, and they would typically have their own way, and there would be like some amount of, with Bristol Hackspace we had a wiki, and we tried to kind of keep that up to date, and we had QR codes on the equipment. I've actually still got a QR code from the CNC machine that I brought with me, and my lathe, and you scan that and it takes you to the wiki of Bristol Hackspace with information about how to get trained on it and who's the responsible people and
fantastic,
etc. Yeah,
very nice.
Finally, a use for QR codes.
Yeah, that sounds good. So as you mentioned, you're now living in Spain. How do you find it over there? Is it
hot?
Hot, yes.
Hot and cold. Yeah, it's like the time between kind of wearing thermal insulation, because I'm just was mentioning earlier, I'm about to move to a different office, but in Valencia, the city, and in Spain in general, it's very normal to have like these blocks, fincas, where you have like 5 floors of flats, and then underneath you have light industrial office and commercial space for supermarkets and garages and anything you want. So that means space is extremely cheap. So I'm renting like a few hundred square meters for a few €100 a month. So it's cheap to rent space. But then it's at the bottom of a building and uninsulated, so it's noisy and cold in the winter, and it's noisy and hot in the summer. So if we hear any background noise, I'll be trying to take care of it. It's not as bad as fire. So in March, we have a festival where like the main thing is exploding bangers. And it's just impossible to have meetings during the end of Fias in Valencia. Just don't
Fair enough. Is it a few days or is it a week? Or?
It's about 3 weeks, yeah.
Oh,
but
wow.
It builds up slowly to like a startling end.
Very tricky. So you've spent a lot of time self-employed, and that's given you control of your time. And we were talking about this earlier. And with that control, you've managed to sort of focus on things that you're interested in more than what customer or employer is telling you to do. Can you talk about sort of what you've covered with that freedom?
Yeah, actually, before I do that, I just
Sure.
My experience at GEC Marconi kind of turned me off from working in companies, and I just thought, I'm not doing that again. I'm just going to be self-employed forever.
Okay.
And that more or less happened. I've been involved in some startups and things like this in teams. I really enjoy working in teams, but it's kind of never been like work, like sign a contract and work for a few years in a big company.
Yeah.
But I think I missed out a lot. I really like the Ampower podcasts where Chris interviews people in the electronics industry, and I've read books as well, like The Soul of a New Machine, and I just read one recently called Sidewinder about the development of the Sidewinder missile. Actually, GEC Marconi, they didn't just do military stuff, but the factory that I was in was the optical sensors, like the cryogenic infrared stuff.
Okay.
But if there's so much you can learn from other people, and I think as a young person I was arrogant. I think young people generally are, but maybe I was more arrogant than most. I thought I'd be able to know everything. And over the years I kind of realized actually that there's nothing like having a good mentor to learn fast and to become very productive and not waste a lot of time learning things the long, slow, hard way, which you can do, and it's a different learning route, and you can learn in a different way, and it's definitely for some people. But looking back on it, I think I worked hard to get mentors from about 5 years ago, and that made a huge difference to me now, having like a big support network of people that I can talk to and ask questions of.
Very nice.
And I think that's something that as a self-employed person you have to take responsibility for, or it doesn't happen.
Yeah. Are you willing to talk more about what you did and how you went about getting people to mentor you? Is it a very frank conversation, for example, or?
Yeah, just being outgoing and meeting people at conferences, but also like online on forums, or like I mentioned the Ampower earlier. Chris has also got the Contractors Consultancy Forum.
Okay.
And be involved in conversations, meet people who are in the biz, actually working, being able to ask questions, and then like if you make a good connection with somebody, then asking could I pay you to have like a series of conversations with me, or could you like consult on this project for me? Sometimes those, often they started off as me asking someone to do some consultancy work on a project that I was stuck on. And then it turned into, we just stay in contact, whenever. I have maybe 4 or 5 people like that.
Yeah, very nice. That's something I'm very conscious of. I am at a position in my career where I feel like I could be useful to people as a mentor, but at the same time, I am very aware that there is so much to know and learn that, looking upwards at others would be very beneficial. So
don't wait to start mentoring, because it's it's great to also be doing that for other people. And also maybe helps you become a better mentee.
Yeah, very true. Yeah. So if we loop back then to the control of your time, being self-employed, and the ability to focus on things that were more interesting to you than perhaps you'd get the chance to do otherwise. Are you willing to just sort of talk about some of the things you've touched on over the years that you might not have otherwise been able to?
Yeah, I guess being able to get into the mechanical and the electromechanical side. I really I got the most experience with electronics and computing, but it's very satisfying to bring something into the world and be able to hold it in your hand. And like building robots, for example, is really good fun and a good challenge, like control and accurate measurement and accurate servo positioning, things like this. And then having the lathe and a mill and a laser cutter, and kind of learning CAD and learning how to generate tool paths, and then setting up Linux CNC and being able to cut plastic and aluminium on that. It's you can do a lot, and it's nice to be able to not just be like on the bench or on the computer, but also to be making chips.
I was going to say
making chips out of metal, not chips out of silicon.
Different kind of chip.
A bit later, yeah.
That's one of the things that has always stuck with me over the years, is that, as you know, working on the computer is fantastic and you can do some really great things, but actually for me personally, as soon as you make a tangible, physical, you can hold it.
Like your first PCB.
Yeah, or even just blinking an LED, or 3D printing, all these things, just really fantastic sort of feeling behind it.
Yeah.
So along those lines, then, with that time, you've also, I think, focused and worked with FPGAs quite a bit, and that was kind of your route towards ASICs.
In a way, yes. Definitely made it easier. So I was doing two projects at once. I was CTO for Digma, which is a Spanish startup, and they make keyboards. The one that I built was called the Digma Raise. I got it on my desk.
As in computer keyboards or music keyboards?
Yeah.
Okay.
It's a split keyboard.
Yeah.
That was actually my first mass-produced. I'd done like a short run, 100 PCBs before, but we'd done 10,000 of these, and DFM, designing to build 10,000 of something is totally different. It requires totally different skill sets, and looking back on it, ideally somebody else.
Somebody else does it?
Somebody else is.
Yeah,
I don't
your
really
cup of tea
enjoy it. No. I'm way more interested in like the prototyping and getting like first life out of something, and then like finessing it into a reliable, sellable product is a lot of hard work and sweating over small details and constant changes, and you have to be very rigorous and keep on top of all the documentation, and it's like not a strong point of mine.
Right.
And at the same time, I was doing an ultrasonic data acquisition system, and that required getting very low voltage readings from ultrasound sensors, and then being very precise about when the sounds happened, so that you could
timing and things,
triangulate where things were coming from.
Is that almost at the phase level rather than?
Yeah, definitely the phase level. Yeah.
Nice.
So it wasn't like it was sampling at like 10 or 15 megahertz, so it wasn't like mega fast.
Yeah.
Had to pay a bit of attention to board layout, but not like DRAM or anything. But then I couldn't find any microcontroller that would let me read 4 12-bit A to Ds and be like guaranteed of their phase.
Yeah.
Looked like a job for an FPGA. And that was kind of, I'd actually been brought in to do a different consultancy job for the same company, which was just building a single channel reader for the same A to D.
Okay.
So I already kind of had done it one bit, and I was like, well, how hard could it be? Do it 4 times in a row, isn't that what FPGAs are good for, doing stuff in parallel?
Yeah.
Oh, what a mistake that was.
So was that
No,
your
it wasn't a mistake. It was just one of those things where it's easy to say, and then
Yes,
when you actually
absolutely.
come to do it, it's
Yeah.
and especially like FPGAs do get into like fairly hairy territory, and it's the difference between compilation and synthesis is like people attempted to make metaphors like the synthesis is like the FPGA version of compiling for a microcontroller, but it works to an extent, but it's not really a true metaphor. And if you believe it too hard, you get into all kinds of things.
Fair enough.
Yeah.
So was that your first FPGA project, or had you done some personally sort of in a learning capacity before that?
Yeah, I'd but was using like a commercial tool chain for the first version.
Yeah.
And then about that time, the open source tool chain Ice Storm got off. Claire Wolf did the reverse engineering and released the back end support for Yosis, so that we could. And then Myrtle Shah did a lot of work on NextPNR so that we could do place and route. And then I was able to replace the commercial tools with open source tools
For that project?
More for kind of my learning projects to start with.
Yeah.
And have you ever seen that talk where I can put my finger on it and get you a link later, but it's basically like somebody showing a demonstration of if you reduce the time of the learning cycle enough, you can go and learn much more quickly. And he did this by various things like drawing computer graphics, and instead of writing some code, rendering it and seeing it as you write the code, you see the change happening at the same time.
Reducing that iteration and the cycle between,
Yeah, and one of the things commercial tools are so bad at is like the overhead. So even if the simplest design might take you 10 minutes to run through it, which is fine if you're an expert and you're doing massive designs because they're taking like a few hours anyway.
Yeah.
But if you're a beginner, every time you like make some small mistake, then you have to wait 10 minutes just like on your LED blinker. It's a real drag. So learn how to simulate and use your open source tools, because then you can get like a 20-second cycle time on a Raspberry Pi.
Wow, that's quite considerably different, isn't it?
Yeah.
Nice.
Yeah, for small projects. So so I did like a bunch of really basic, small, simple projects on the open source tools, and then ported over this commercial project later.
Okay, very good.
Yeah.
So then from the FPGAs, you stumbled across the Skywater, Sky 130 PDK and things, and sort of got into the ASICs.
There was like a missing step there, which was I was at the World of Open Source Hardware conference, and Tim Edwards, who's at eFabulous, shared some work he'd been doing on an open source chip.
Right.
And he'd used Qflow, which is like an open source ASIC flow that he was maintaining. I don't think it's still being maintained. And I saw a tweet by Adam Zaloof, brother of the famous Sam Zaloof, who builds chips in his garage.
Yeah.
And he'd taken the Pong, I think it was Pong netlist, and run it through and got like the GDS for Pong. And it was like 200 micron square or something. It looked really cool on Twitter. And I was like, that's cool, I'm going to try that. So I took my clock, my VGA clock, which was one of my simple FPGA designs, and ran it through and got a result and tweeted that out. And there was a lot of interest, a lot of people interested in open source ASICs and open source FPGAs. It's got a nice community, nice like group of people.
Yeah.
But that probably would have been the end of it had Google not sponsored Tim Ansell at Google driving the sponsorship of the open source shuttles, because I actually did spend like a few weeks putting together a workshop, because I've done loads of trainings, like I said, science and technology communication, lots of training. Yeah. So I thought I could do a workshop to show people how to make a chip, and we'll make a chip at the end. That would be cool. But it was $10,000 just to get the chip. So I just thought that making a course was going to be not a realistic thing for most people.
So just before we go too much further, how much before this this process was it to get a similar sort of product? That's $10,000 now. Would it have been considerably more?
No, 10,000. That's how much it was without this skywater PDK.
Okay, right.
We're not going through somewhere like Euro circuits.
Right.
Like I could just go directly. I'd have to sign an NDA.
Yes.
I'd have to probably bring my own tools. There was a lot of stuff I didn't know how hard it was going to be at that point, but just the cost put me off. Yeah. But then the Google sponsorship meant that there was a chance to get a free chip.
Free. Look at that.
Oh yeah, look at
Fantastic.
that. Die in a cube. I keep it on my desk to fiddle with.
Did you put it in the resin?
Yes, not very well. There's lots of bubbles.
No.
Yeah. I found someone who can do it a lot better now.
Yeah. For next time.
This one. Yeah, I'm working on a kind of souvenir.
Look at that.
There you go. That's better.
That's amazing. Well done.
Yeah, so that kind of, then I thought, oh, well, then I can do this then actually, because I don't have to pay for the chip. I'll learn how to do it. We got the new tools, OpenLane. Mm-hmm. We got an open source PDK, so you didn't have to sign an NDA. And that was why you may now have, depending on like what Twitter bubble you're in, but you may have seen like photos like this on Twitter, because people are posting their GDS now, like the files that we send to the Foundry. Like Gerber files if you've done PCBs. But before, you wouldn't have been able to do that, because by sharing them, you're breaking the conditions of the NDA.
Even at a sort of a high image level, where obviously you can't do it.
Yeah.
Okay.
You could print it out and hang it in your office, but you wouldn't be allowed to like
no public.
It.
Yeah, interesting. Okay.
So, yes. Olof Kindgren made the joke that we're just about getting bored now of GDS photos, because everyone for the last year has been hammering social media
commonplace
GDS photos. I'm still not bored though.
I don't know. I'm not bored yet. Keep going.
Yeah.
So this is a design this is a course that you've put together to help people through getting sort of a step up on the process. Is this you doing it for the first time and sort of coaching others along as well, or is this something that you've run through before and you've proven your workshop and your material effectively, and then given them the
so kind of like the process that I went through with kind of getting some GDS and then like running a simulation on an AND gate and then looking at the ASIC flow. I was posting I kind of like to learn in public. I did the same with FPGA stuff as well. So you get people helping and also find out where the communities are and this kind of thing. And it's good for documentation to go back on things, and keeps me maybe a bit accountable. Like if I got like a Twitter thread with 15 threads, like getting to the culmination, and I want to get that last thing of it done.
Yeah, absolutely.
But I was getting way more engagement on the social media for the ASIC stuff. And I just thought this could be a good opportunity here, because I had one job that was just a contract coming to an end. Mm-hmm. And instead of looking for a new contract, I thought maybe people are interested in a course, because now there's this option to do a cheaper course. Mm-hmm. So I did the Remoticon 2020 when their Supercon was cancelled due to COVID. Mm-hmm. And had a sign-up form at the end of my presentation. And I think like 10,000 people watched that video, and then I had like 200 people sign up who were willing to pay $500 for a course. So
has that converted into 200 people actually on the course and pushing through?
In the end, yeah. I've just
amazing.
Just like this last month signed up the 200th person.
Fantastic, well done.
Yes, but I sold the first 10 tickets before I even had the course. It's like
that's a bit of pressure there as well.
Yeah, it's another thing that I've changed over the years. Is like I used to try to get everything perfect before like putting it out there and trying to sell it, or trying to see what the value is. Yep. And now I try to like sell an idea before necessarily I've actually got everything in place to see if there's going to be demand, how much, because it takes a long, like we talked with the keyboard, it takes a long time to get something in a good enough shape to make it commercially viable. Yeah. But selling 10 tickets to a course kind of then paid that $5,000 paid for me to spend a whole month spending every hour of every day putting together the best thing that I could. And then since then, it's just been kind of like gradual improvement and updating as the tool had changed. And then we've made like different changes, and the shuttle runs, the way we do the shuttle runs is changing gradually. Yeah. But
Fantastic.
yeah, I'd say it's kind of like 50% of, or maybe 40% of my time is doing the course.
Okay, and so that's effectively your job, or 50%, 40% your job.
Yeah, so yeah, CSO for Yosis HQ.
Okay, yeah, I saw that. It's very good.
So if anyone out there needs formal verification tools, then
Hey.
I'm a founder member of ChipFlow, and we're aiming to use the open source tools to lower the barrier to entry for product companies to design their own chips. Because we think there's going to be a new market emerging now that it doesn't cost $100,000 a year license for the ASIC tools. And I'm also doing some contract work for eFabless because they've got an exploding community and lots of people who need help. So I'm doing like videos and documentation and community support for them.
Okay, that sounds really good.
So it's all kind of open source EDA, FPGAs, ASICs, community, videos, documentation, teaching, training. That's my bag.
Very good. And you enjoying it?
Yeah, I love it.
It's fulfilling, etc.
Yeah, really. Yeah, I had like the whole engineer thing for me was like, I don't know, I got like obsessed with the word. Like I wanted to be an engineer, but I didn't really know why. And then I realized afterwards, I'm not actually a very great engineer. There's lots of other people that are a lot better at every part. I'm like a generalist.
Yeah.
Yes, but I've got a good network, so if I get stuck, I can ask an expert.
There you go. So in terms of the course, then you've put, I think one chip has come through and out the other side. And can you talk us?
That's this one. Yeah,
that's that one. There you go.
Yeah, let me just swing the camera around and show you this.
Okay, sure.
On the desk. Yeah.
Oh,
so that's my clock, which is great because it worked on the FPGA. It worked in the simulation. It works on an ASIC as well.
Yeah.
And that's the chip in the middle. So that's like this.
Okay.
The little rectangle in the middle is the actual ASIC. It's a 60-pin 0.5 millimeter BGA.
Yep.
And it should have been plugged just straight into a small board, a bit like the size of this one.
Okay.
But we had some problems on MPW1 tool chain configuration that meant that it didn't work. Basically, it didn't work as planned.
Right.
Yeah. So we had to do some funky stuff. And when I say we, I mean Sylvain Minot. He's like another hacker extraordinaire who kind of built a bring-up system that allows us to very carefully control the voltage. So by undervolting, basically the chip had, I won't go into too much details because I've got to like explain this thoroughly in other videos, but
right.
The tool chain had a misconfiguration bug that meant the clock network wasn't as good as it should have been. So there were hold violations, which means that the flip-flops don't have enough time to latch the new data, and it can't be solved by changing the clock frequency.
Right.
But if you undervolt the chip, you can like slow down how fast things work, or speed up things, or slightly change the performance of the MOSFETs and the flip-flops. And if you're lucky, on 25% of MPW1, you can undervolt it at just the right level to get something to work.
Amazing. How was that one discovered?
If you see my designs here, they're all very, it's just like the darker squares.
Yeah.
Oops, whoop. Those little squares.
Mm-hmm.
They're very small. They're like 200, 300 microns by 300 microns. So like 0.2 millimeters by 0.2 millimeters kind of size.
Yeah.
And so even with a screwed up clock network, they still work because you can't actually get too much skew on a clock network that small.
Right.
But we couldn't get the inputs and outputs to work because they're controlled by the RISC-V coprocessor that's on here, and that was messed up.
Right. Okay.
So basically, it was like a hacking exercise of getting that volted and clocked just right that we could run some very specially crafted assembly RISC-V firmware that would get enough of the pins in the correct I/O position.
Amazing.
So Sylvain did 90% of the work on that, and That's why I've got my clock on my desk. So thanks,
Well
Sylvan.
done. Yeah. Is that a technique which was suggested to you by them in inverted commas, or is this something that you have had to find out as a group? How
it's a
and
good
why has it
question,
gone
actually.
wrong? Let's sort of, because a scale like this, you can't poke it with a scope probe, for example, see what's going on.
No. Although we have decapped them, and we're like working on a focused ion beam fix where we're going to cut wires inside the chip and then wire bond them out so we can control them externally. So that's like that's something I'm working. Yeah, that's something I'm working on, like just as a experiment, basically, with a guy called Olivier at Texplained, who does chip reverse engineering.
Amazing.
But yeah, coming back to this, I'm not sure where it came from and who suggested it. And I've spoken to very experienced ASIC engineers who thought it was a myth, and that you could, because traditionally the common belief is if you have a hold violation, that's it, it's a write-off. Just fix it and send it to get the chips made again, and just throw away the ones you've got because they'll never work. Which is probably true for most designs, but because I had so simple ones here. Once we finished the IOs to work, all of my designs inside worked as expected.
Amazing.
Yeah.
That's been a bit of a relief.
Yeah, it was because I was like, when the news came in, I was like, oh shit. And then I like made a video explaining it and was had fun with the thumbnail. It's like me screaming next to a gravestone, coming out of the top of a ship. But it worked. Mine worked. Hardly anyone else's did. I think the only other person that really tried was Sylvan.
Yeah.
And he got like a fraction of his design working, like a small piece, but not the big complicated stuff.
Oh.
And as far as we know, no one else is. I think 2 or 3 other people have attempted, but I haven't heard that they've actually got anything working yet. So,
okay.
Yeah, I mean, I've got like a 4-layer stack up here just to get the clock working. So,
I was going to say, so that board there that the chip is actually on is a little small carrier square, and then you've
carrier
got
on a
2
carrier
other boards
on a
underneath
carrier,
it. Yeah.
And then the icebreaker from 1 Bit Squared from Esden. Hi,
Saw that as
Esden.
well.
Love the icebreaker. So that's what's doing the careful undervolting, and then it models flash for the Pico RV32 to read the firmware off it, and it counts because the Pico RV32 is execute in memory.
Yeah.
So you can see what the CPU is doing by its memory reads.
Accesses,
So by instrumenting the memory model on the FPGA, Sylvan can count how many successful instructions are executed on the CPU at a given voltage and then plot a histogram.
Amazing.
And then you'd be like, okay, so at 1.37 volts, it managed 1,000 in a row, and that 1,000 is enough to load 1,000 handcrafted RISC-V assembly instructions to set the IOs up.
That sounds terrifying. Such a massive extension to the project.
But, and like after a year of waiting as well, like 3 months of like heavy duty work and then a year of waiting.
Yeah. So that physical chip there, is that am I right in thinking that's got a design from each of the people on your course? So
no, because on MPW1 it was like this one, which I did with like 4 friends or acquaintances, like people that I knew that were interested.
Pre-course.
The first design that came from the course was MPW2, and we're expecting those chips. They're out of fab now.
Okay.
So we've got the wafers out of the factory and they're being bumped, and then the next thing is them to be diced, and then eFabless are going to mount them on PCBs, and then they're going to send them, and we're expecting them sometime in July, so in a month or 2.
Fingers crossed.
So fingers crossed.
Yeah. Have you been able to take your lessons from the clock issues that you've had and sort of tweak your, I don't know what you'd call it, but tweak the output of your tool chain to do something that's a little bit more sensible and might work better?
I think the community has a bit. Like I contribute a bit, but more in terms of documentation and opening issues and filing test cases and bug reports. But I don't really contribute much to the tool chain. But Well, I mean, when you run OpenLane, you get about 350 intermediate files, as well as the final thing that you need to actually send to the factory. And it's very different. And also, there's like tens of thousands of lines of logs,
Right.
and
It's very dense to try and pick it
hundreds or
apart.
thousands of warnings. And you don't really know which warnings are important or not important.
Yeah. Okay.
And when we went back over the timing issues, we actually saw in the report logs not a warning, but actually it might have been a warning. It was just like saying something like clock arrival time not set, assuming 0.
Right.
And that should have been a red flag to people that know about clock trees and static timing analysis and flip-flop setup and hold time. But at the time, that certainly wasn't me. I was just like, yay, it got to the end without breaking. Send the files.
Try it.
Yeah. Just quickly wait for a year.
Yeah. Just quickly wait for it.
Just quickly wait. Yeah.
Very good.
Yeah.
Okay.
So yeah.
Sorry, I was going to ask. You've got this 60-pin BGA, which presumably a number of those pins are power, ground, etc. A number of them probably clocks and whatever else, and so you have a smaller number for
about
your
40.
IO, 40. So that then is split per design, or have you got some way to sort of multiplex the pins? And
yeah. So what we did on
designs?
MPW1 was we multiplexed everything so that the kind of long bar at the bottom,
yep,
there in the top, there's like the 4 designs, and then underneath there's a kind of long purple thing. That was like a multiplexer with, I think you need, because for the 40 IOs, you've got 40 ins, 40 outs, and 40 output enables. So you've got 120 pins.
Yeah.
And then for the logic analyzer, you've got 300. For Wishbone, you've got like another 300. So there was like 1,200 pins to multiplex or something. So yeah, I needed a big block just to squeeze all the pins around the outside of it.
Yeah.
And for MPW2 and onwards, what we moved to a like a high impedance bus architecture, a bit like I2C.
Yeah.
Where if your device is, or SPI, if your device isn't doing anything, is like not addressed, not activated, it's just sat there with its outputs set to high impedance mode, ignoring everything that's going on. Yeah, which makes routing easier. We can pack more designs in. So now we're getting like 16 or so designs on each shuttle run.
Okay. And then some way to effectively enable one at a time. And
then the firmware runs a bit of firmware that basically activates each design's tri-states one at a time.
Nice. Sounds good.
Yeah, hopefully it's going to work.
Fingers crossed.
Yeah, because otherwise there's like, another 4 chips that are all made with the same pattern, and we're still waiting to know if it works or not. I mean, it simulates. We've done gate level simulations.
Okay.
There's no reason to think that it won't, apart from unexpected stuff that we faced in MPW1.
Okay. So it sounds like you've got some kind of overlap between sending off the design files for MPW2 versus receiving the MPW1 back. So the design files went off before you got the first chips, is that right?
Yes. Yeah. So we've sent for MPW1, 2, 3, 4, and 5.
Oh, wow. You sent that many.
We've only received MPW1 back.
I see. I hadn't realized there was quite so much overlap.
Yeah. So I'm just getting an experiment ready now for MPW6 tomorrow.
Okay.
And then when we run the experiment, it will help us to characterize a bunch of interesting things, but we're going to have to wait, probably 8 months at a minimum to get those test results. So it's definitely like a measure many times, cut once kind of scenario.
I used to work for
about that short feedback loop.
Yeah, absolutely.
It's not a good one for ASICs.
No. I used to work with a company who, long ago, they actually decided to, instead of using a processor, they put their product into an ASIC, and it was sort of one of the big high ups made a decision to do it, and I think it sort of became quite painful. And they were commenting about how it was very susceptible to ESD, and I think they spec'd a 32 kilohertz clock, when of course they meant 32.768. So the RTC ran slow, all this kind of thing. Um, I don't know, but is a lot of that sort of resolved? Are ASICs now quite robust things, similar to sort of normal micros in inverted commas?
There's no reason they shouldn't be, but
Is that kind of down to how you spec your IOs, I guess?
yeah, like there's kind of it can be helpful to kind of split the ASIC world into two roughly.
Okay.
You've got digital stuff where you're just taking your design that already works on an FPGA, running it through OpenLane, and like sending off the files onto the Google Shuttle. And that there's no reason that shouldn't work. You have to kind of jump through a few hoops and like be a bit more careful on timing. And you should, given that you're going to wait 8 months, you should you should make sure that your test coverage is pretty high and etc. But then anything like A to Ds, D to As, GPIOs, clock drivers, power supplies, you can even consider the wiring or the standard cells. All of that is the kind of the analog side. And that is, you tend to like, you do that in a different way because you can't simulate it with a digital simulator that is optimized for millions of cycles. When you simulate in Spice or Zeiss, things are, you might like have to wait an hour to just let the program calculate what the initial conditions are at the inputs of your chip before you can simulate the first clock cycle.
Wow. Okay.
So this, like the experiment that I've been doing was taking like a couple of hours to simulate 8 nanoseconds of time.
Right.
And I wanted to measure the speed of a ring oscillator.
Yeah.
So I needed to get like 3 or 4 oscillators, like cycles out to get a long enough period to measure an average. Yeah, so you want to avoid that if you can, but it's inescapable for things like IOs. And to answer your question about ESD and stuff, with the open source tools, one of the things that really needs a lot of work on is the open source IP, intellectual property. I'm not sure, there's probably gonna have to invent a new word because open source intellectual property doesn't quite sound right.
It's a bit contradictory.
Yeah. But you need like an IO block that we can all use. It's got to be open source. And the ones that we've got are 25 years old. They're from like Skywater used to be Cypress, and it's from an old Cypress process.
Right.
And we're using these IOs that are like 20 years old, which are still good, and you can still do like gigahertz stuff in the chip.
Okay.
But you can't do gigahertz across those IO pads, and
Through
we
the
don't really
outside
know.
world.
I don't really know what the ESD. There's a lot of characterization stuff that is still work in progress or missing at the moment. Yeah.
So when they eFabless put the chip on a board for you, it sounds like does that board then come with a lot of protection and power supplies and things, or is it really just a carrier board to give you access to those pins?
For MPW1, we just had these boards and the chips, and we had to solder the chips ourselves.
Okay. I was a bit surprised when you said that they put them on for you. So
yeah, well, in the future, as like part of their thing that you get is 50 chips and 3 boards, I think, or maybe 5 that have the chip mounted and like a USB to serial and a flash and an oscillator.
Oh wow, okay.
And a power supply. So you should be able to plug it into a computer, use the same firmware that you used in your test bench, load that on over USB, and then the chip should be doing the same thing that you saw in your simulation.
Yeah,
that's what should happen. Yeah,
amazing. Okay, I hadn't expected that at all. I presumed it was much more, hands-on, and you have to do a lot when you receive the chips to do anything with it.
Yeah, that was the case for MPW1, but that was only true because of the hold violation mess up.
Oh, I see. Okay.
Yeah.
Interesting.
And then you'll have your other 45 chips that you can put on your own custom board, and because everything is open source, you can just fork the KiCad repo and start your business.
Brilliant. Okay. It's daunting. I have to admit, even sitting here just talking to you about it's daunting as a prospect.
No, it is. Yeah, and like we mentioned this earlier, but it's worth saying that the FPGA experience that I already had made going into the digital ASIC side much more approachable, because half the job is getting your intent into a hardware design, which is totally different to writing software, and simulating and code, like running it on an FPGA and all this business. And then you don't really need to do that much to go to an ASIC. With an FPGA, you can pretty much guarantee that your flip-flops are all going to be 0 at power up.
Okay.
Whereas with an ASIC, you want a definite reset that guarantees everything starts up correctly. Yeah.
Interesting. That's a whole topic on itself, I'm sure. Power and reset type stuff.
Yeah, that's a vast simplification. You've got to remember also that I've been learning this for like 1.5 years, so it's not like I'm any kind of expert at all. I'm just happy to be, learning and making mistakes in public.
Very good. Well done. We've got sort of just under 10 minutes left. Is there anything in particular you'd like to talk about, or any sort of slides you might like to show? I think you had some presentations ready. And while you're thinking about that, if anyone has questions, please feel free to ask them or try and get them answered.
Yeah. I wouldn't. Yeah, there's. I'm working on an interesting project at the moment that's interesting for quite a few different reasons. It's got a lot of different overlaps. So it's working with I'm at the moment doing most of the work, but I've had help from like 4 or 5 different people. So it feels more of like a group project. And it came from being introduced to a guy called Teo. That was an introduction from Tim Ansell again. And he is doing a PhD and working on optimization of hardware adders. And we did a live stream that you can check on my Zero to ASIC YouTube channel if that sounds interesting. And one of the interesting things that he shared was he took a RISC-V processor, put it on and simulated it and instrumented it so that he could see how many add operations were done in a Linux boot. Okay. And 70% of instructions resulted in an add. Wow. So adds are used in everything. They're used in multiplies and divides in the ALU, but also all spread throughout any CPU or any design.
Yeah.
They're like a really fundamental part of digital design. And there's many different types. There's like a world of research on this. And there's a whole kind of space that you can explore. You can go like, I want small, but it's going to be slow. Or I'm going to go fast, but it's going to be big and use more power. Or I want like a mix in the middle. Or if the bottom 10 bits can be slow, but the 12th and 13th bits got to be blazing fast, whatever. And he's got like a Yosis plugin and a Python library that lets you choose what type of adder and how wide you want it to be.
Okay.
And 4 different architectures. And then we've got the Yosis parallel architecture, which is the one you get by default. And we thought it'd be cool we've got like the simulation results. A guy called Proppy did a very interesting Jupyter notebook in the cloud that Teo leveraged to do all the simulation. So he could actually get PPA, power performance area results on the cloud without having to mess around with the tool chain, which is great. And also in his paper, now he can just have a link to a Google Colab, and someone else who's interested can go there and reproduce his results. So it's amazing for academia and for sharing results.
I was going to say, the open source world is for that purpose, it's awesome, fantastic, isn't it?
Yeah.
But
we thought it'd be good to actually characterize how fast those adders are.
Yeah.
So I've been working on that, and I've been getting input from a lot of very experienced people who are helping me to design the test circuit. So maybe I'll just share my screen for a minute.
Just before you do that, we've got a couple of questions
okay.
from I Love Scotch. We have how many equivalent logic gates could one place in their logic place? I presume this is within the group, the course. Is there a figure you can put on that, or is that a bit awkward to give an answer?
Yeah, it's difficult to say, because unlike an FPGA where you have like every logic tile has a lookup table and a flip-flop, and it's all laid out for you. With an ASIC, it's a blank canvas. And if you did a design using only inverters, which are like the tiniest standard cells, you'd be able to get in like 12 times more than if you did a design using only flip-flops.
Okay, interesting.
So it depends if your design is register heavy or logic heavy. And people who are used to writing for FPGAs tend to use a lot of registers because they're kind of free in one sense. Whereas if you're doing ASIC stuff, then you would be trying to avoid them if you could, because
Yeah.
they use up so much space.
Very good. And then a follow-up question. We got a question about maximum frequency for the project.
Same
saying
answer.
that
It depends.
Yeah. And you mentioned earlier you could get gigahertz internally, but again through the IOs, you're very limited.
Yeah. So Thomas Parrier's doing 3 gigahertz amateur satellite radio with a careful hand laid out analog design. I've got a ring oscillator that I'm using to characterize these adders I was mentioning.
Yeah.
And if you have 21 inverters in a loop, that ring is predicted to oscillate at 650 megahertz.
Okay.
But as soon as you like build a state machine and have flip-flops and registers and other stuff around it, then
all the timings add up. And
so if you take something like Pico RV32 or Vex RISC-V, which are kind of well-known RISC-V CPUs you could run on an FPGA, you'd probably get them up to maybe like 50 megahertz on this process.
Interesting.
Yeah, but like a real kind of custom something, hundreds of megahertz or gigahertz.
Very good.
Yeah.
Have you got a minute to show your slides? I'm very conscious we got to stop quite sharply at 4 or just before. So
yeah. I'll just share this adder. This is the development repository. No, not that one.
Put your screen on.
Yeah, so this is the work that Teo did with the different type of adders and the different maximum frequencies and areas. And the idea is now we can choose which one we want.
Interesting.
And this is the circuit that we've come up with. So we have a ring oscillator here, and we can measure its frequency by counting it in this counter. But then we can turn off this loop and insert the adder into this loop.
Okay.
So then we can see how much slower does the ring oscillate when the adder is in the circuit. And we can choose to put the ring into any bit of the input and take any out of the output, so we can check each bit. So that's going to hopefully let us measure to see whether the results that we get from the process actually match up with what's predicted.
Yeah, very interesting. So I presume that the gates you were showing there, the buffers with their enable pins, that's all under the control of your coprocessor effectively, is it?
Yes, yeah. So we have
so that's the benefit of having this little slab of logic that's a little bit more intelligent. It can run instructions, gives you the ability
so
to...
if I come up to here, I've got a little bit of C.
Yeah.
With all like the definitions of what all the different things do. And then down here is basically setting up that ring and the adder, and then running the test and then waiting until it's done and putting the output on the output pins.
Yeah, fantastic. Very good.
Yeah.
I think it's about time to wrap up. Thank you very much for coming on. It's been really, really interesting to talk.
Yeah, it's been cool to talk. Thanks for having me.
So it's fantastic. The course just looks amazing. Jealous, to be honest. I was very tempted, but limited on time, etc. So
yeah. Well, when you get a holiday, you can come on a course.
Well, yeah, quite. Anyway, thank you very much for coming.
Yeah.
Next week we got Graham Sutherland, and we'll be talking about EMF camp and lasers and things. Aside from that, goodbye from us.
Bye-bye.